yesterday I said something, you always want to do stoichiometry first, followed by adjusting things for equilibrium. The stoichiometry essentially means talk about the things that have the biggest equilibrium constants. Water has what for its equilibrium constant? 10 to the minus 14. What did magnesium hydroxide have? 10 to the minus 11. So this was bigger, so this is the one I did first. Then I went back and looked at water. Over here, water was 10 to the minus 14 for the K. This one was 10 to the minus 33. This was much bigger, so I should talk about the water first and then talk about the aluminum hydroxide. You always do things with the biggest K first. Then you go to the other things. And most of the time, what we've ended up doing is ignoring the ones that have the smaller Ks. Most of the time we ignore water. But here I'm just justifying why we ignored water. Because now I can see how much hydroxide I actually got from the water. Yes?
Well, some of the common ions, it'll be like a saturation, so you're not sure what the K is for the other one.
Okay, I talked about, but I'll come back to that. I know the question you want now, and I will come back to that in a minute.
Okay.
I just want to finish my discussion here because this is illustrating something. These are all supposed to educate you about what's happening in these systems. And because the question always comes up, why did I ignore that? Why did I ignore this? How come in this problem I have to use water. In this problem, I got by ignoring water. When I talked about I ignored the water. And I got the right answer. When I talked about this, here it is again. And I said pH equals 8, and I was wrong because I ignored the water. This is 10 to the minus 8 molar HCl. That's the problem I started off with weeks ago.
Is it still bigger than negative 14?
The KW always stays the same, 1 times 10 to the minus 14. Well, I don't want to confuse you here, but basically that does change slightly with temperature. But overall, the problems we do, we assume it's 1 times 10 to the minus 14.
But then I thought you would ignore it if it's...
Here I ignored it, because this is aqueous HCl, right? And it was 10 to the minus 2 molar HCl, and I calculated the pH. And I used the concentration because this gave me associated completely, so that was the concentration of H plus, and I didn't worry about the water, I just said pH is 2, because it's the negative log of the hydrogen ion concentration. Then I gave you this problem, and I led you up to this, and a lot, well, not too many people, because they're looking at me, and anytime I get to something really easy, they said, there must be a trick there somewhere. And somebody hollered 10 to the minus 8, I did hear one person say it, usually about 3 or 4 people say it. And what's wrong with that? This is basic. 10 to the minus 8, or pH 8 is a basic solution. There's no way you can dilute an acid and make it basic. It's going to get less and less concentrated, but it won't be basic. Okay? And I said at the time, the hint was, and I said, work on this over the weekend, and nobody worked on it over the weekend. And I sort of gave you the answer, but I said the hint was you have to use water. Okay? Because then you have, and I'll write fancy now, for the hydrogen ion, is the concentration of hydrogen ions from water plus concentration of hydrogen ion from HCl. True source of the hydrogen ion. I couldn't ignore the hydrogen ion from water. Up here I could. In this problem, I couldn't ignore the hydroxide ion from water. In this problem, I could.
Wait, so you're saying pH, so...
Why could I? I'm gonna justify again why I did it, because I'm gonna calculate how much hydrogen ion I got from the water, from the hydroxide ion. And I said, okay, here's my approximate solution. This is the hydroxide ignoring the water. Then I want to find out how much hydroxide ion should I really have if I don't ignore the water. Okay? So I started off putting in the kW for water. Well, I didn't put in kW, but I did my IC. My next one would be E. So what did I do here? I did my E. This is X. Here's my E. Plus X. Okay? And this one's still X. So this is my setup for the problem. And I'm going to show you why I ignored the water this time. There's always cases where you can ignore it and cases where you can't. This was one where I couldn't because you asked me for the common ion problem. Everybody's all set with this. I don't have, oh, I know I can go way over here. That's why you like rooms that have boards that go all the way around. That's why the math people have their boards going all the way around and people have to keep changing their chairs to follow them. Okay. So, I'm stuck with this board. Yes?
So you gave me the impression that since like for this 10 to the negative 8 molar, you gave me the impression that since water is 10 to the negative 14 and 10 to the negative 8 is less than.
Wait. That's not, let me come back to this. I'll save that like that so I remember to come back to it. Because that's not quite what we're saying.
Okay.
Let me go back and finish out this thing. We know this is not right, so I'm going to ignore this. But the statement that I made that is correct is you always want to work with the larger equilibrium constant first. This is the larger one when you compare it to this, which is 10 to the minus 14. Okay? Coming back to this problem. This is the larger one because it's 10 to the minus 14. This was 10 to the minus 33. So I can't ignore this one. I start with it. Now what I'm doing, and this is just justifying why I can do that. I want to find out what I actually have in terms of hydroxide ion from water. This is the hydroxide ion I get from just thinking about the magnesium hydroxide. Okay? So now let's solve this problem. Kw is equal to hydrogen ion times hydroxide ion plus X. Okay. And I know Kw is 10 to the minus 14, so X has to be pretty small. Now don't confuse making an approximation to solve a problem with what I'm saying here about which is more important in terms of reaction. Solving a problem is just trying to find a number for X by doing arithmetic or math or something like that. Okay? So I did approximately, I can expand this out and do the quadratic equation, but I really don't want to.
Wait.
What?
Wait, so the Robert said comparing it, maybe see which one you look at first. That's not related to the ignoring thing, right? Like ignoring water.
Yeah, well, I'm ignoring water when I did this solution here. Okay? And now I'm going to justify why I could ignore water. Okay? I don't like to just make statements and then say, I'm not going to justify. I come back and do it mathematically to show I was correct.
I believe you.
So, I don't care if you believe me or not. I could sell you a bucket of gold or something and you're impressed. I don't know. But, so I always like to prove statements when I make it. So that's what I'm doing. Now the other thing that people are mixing up here, when I'm solving this is a quadratic equation. I could expand it out and get the exact solution, right? But I'm too lazy to do that. So I'm just going to solve it approximately. That's not the same as ignoring something else. But I'm going to show that when I solve it, I was okay to ignore the water. Because now I'm going to solve this. And I get x. I'm going to ignore this. Remember, I said this is the only one I don't give you. You should always know this for kW. Equals. There we go. I get 3.2 times 10 to the minus 11. But this is going to prove what I was saying. So again, this X represented the hydrogen ion from water. That's what the subscript says. That's the hydrogen ion that I got from water. Now each time water dissociates to give me a hydrogen ion, it also gives me one hydroxide ion because they're formed in a 1-to-1 ratio. So I got this much hydrogen ion from water. This is how much hydrogen ion I actually got from the water also. So right here, when I solve this problem, I did erase something I wanted. When I solved this problem, I didn't ignore 10 to the minus 7th, I actually ignored 3.2 times 10 to the minus 11th. So if I wanted to really get the actual hydrogen ion, this would be this, and then I'd have a bunch of zeros, and finally I put in my 3.2. Okay. So coming back to everything, what I have here are two different base dissociation problems. One, this is relatively strong, so the K is bigger than KW, and I ignored the water. This one, the KW, the KSP is much smaller than water, so I couldn't ignore the water. And then the problem, which I won't give you, suppose KSP is about the same size as KW. What do I do then? A set of 6 simultaneous equations. Oh. That's why I won't give it to you. I'm happy if you can solve a pair of simultaneous equations. That's what I tell my 1A students. So we're not going to do that problem. Where would you see that problem? When you go into quantitative analysis, the next course has this, because they do a lot of these problems doing even fancier arithmetic and more complex systems. So I say some of these things. I used to teach quant, and we just never got enough students now because the medical school said they don't have to know quant. You know why they said that?
Why?
Because we can weed you out with 1A and 1B in organic. The whole reason you have to take all these courses is the medical schools don't have to fail you out. They want the chemistry instructors to do that.
You did a good job.
And I said,